hard. Where is everyone? Okay. Oh, we have equal number of students online than we do face-to-face.
You said equal number?
Yeah, there's 2 here and there's 2 online.
Awesome.
Does that scare you away, Dan? You want to stay coming online now? Did I talk about nuclear war and it scared you away?
Yeah, I don't know. I guess I don't know. I guess so.
I'm just kidding. I don't care. I'm playing. But how you guys doing? Anybody have any questions on anything? Anything to talk about? And you guys can see the screen, right?
Yep.
Okay. All right. So this stuff is not on the upcoming test. So this is the next section as we're moving on. And so, and although today I'm going to talk a little bit about chemistry and society, and the point of this chapter is about acids and bases. So, and here are some common acids, and start with hydrochloric acid, and this is what it's used for. So clean metals, do with food, refine ore, and it's also stomach acid. So our stomachs, we actually make hydrochloric acid in our body, which is, I think it's pretty amazing. I mean, such a strong acid. And so our stomachs, and I'm pointing, I guess you can't see in Zoom, I'm pointing to my stomach. The way that it's made is, we call it a proton pump. It pulls a hydrogen ion off of water, and your stomach transports it across its membrane. So this is important for a few reasons. Well, I mean, as far as like, I don't know if you guys get this. Sometimes I get acid reflux. And so I'm sure everyone's taken antacids sometime in their lives. So for antacids, the way they work, it depends on which one you use. There's Tums and Rolaids. Tums is calcium carbonate, Rolaids is magnesium hydroxide. Those just neutralize the acid, so they just outright destroy the acid. You can also take H2 blockers. So famotidine, that's Pepsid AC. That one is called an H2 blocker. So, and if you study, I forget, does anybody want to be a pharmacist in this class? I didn't think that we had any pharmacists.
Me.
Oh, you do? Okay. Oh, so you like this stuff.
Maybe. Yeah.
So it's interesting the way that I mean, what we know about how the body works is kind of scary, how little we know. And so if you do study those like different pathways, and it's kind of like, they're almost like guesses. So one of them is the histamine response. And so when I say the word histamine, most people think of H1 histamines. And that's like, if you get a runny nose, like if you're hay fever, right? If you're allergic to something, you start having, your body releases chemicals called histamines. And the H1 response, that's the runny nose, just scratchy throat. That kind of, under severe cases, H1 can cause, their H1 histamine 1 response can cause anaphylactic shock. So H1 blockers, so like Benadryl is a very common one. Benadryl is, I think phenylhydrazine, I think is what it is. Loratadine, that's Claritin, is another one. Allegra, there's all sorts of them. And they work by what we say breaking down the H1 response. There's also H2. H2 deals with your GI tract and can also deal with your skin as well. So, and so Pepsid AC, famotidine, that works by changing your H2 response. And the best way I would describe that response is, maybe I'm showing my nerddom. I don't know if you've seen the movie Star Wars. And in one of the famous scenes, Obi-Wan Kenobi goes like, "These are not the droids you're looking for." He goes like this, kind of like, no, and like, "These are not the droids we're looking for." It's the H2 response is kind of like the Jedi mind trick to your stomach. It's like, you don't need to make acid. And the stomach's like, I don't need to make acid. And then it takes your acid level down. And then the strongest type of antacids we have are called proton pump inhibitors. And how those work is it stops the ability for your stomach to make acid. And it shuts down the entire process. And that's not a big deal for us humans because we have a pretty small digestive system compared to other animals. If you look at apes, they got these big bellies. It's because they got a really big digestive system, and they have a big digestive system because they need it, and they need it because they don't cook their food. We humans, we need to cook our food. I mean, there are some things we can eat raw, but we're not built to be wild of sorts. We need to have, and I mean, even our ancestors, you know, if you look at the evolution of humanoids, they cook their foods too. So I mean, we need to, and because of that, we don't need to have a very strong acidic stomach to get the nutrients from our food because we cook it. Other animals though, like cats, and basically every animal needs to have a really acidic stomach because they don't cook their food. But anyways, that's hydrochloric acid. Oh, it's also called muriatic acid. So have you ever heard the word muriatic acid? That's hydrochloric acid. So moving on, sulfuric acid. And so sulfuric acid, this is also known as battery acid. So a lead acid battery, that's a car battery, is a lead acid battery. That one is, well, if you ever, I mean, if you've ever picked up a car battery and you move around, you can feel something, you can hear something sloshing inside of it. That's sulfuric acid. And you can see, what is it used for? Fertilizer. Fertilizer is the next line to that. So if you look to human life right now, so does anybody want to guess what percentage of the population is geared towards food production? Like what percent of the population feeds the rest of the world? Close. It's about 5%. And it depends. You can argue, you might be able to argue 10%. You can argue maybe as low as 2%. So it really depends on what you want to argue, because you could argue close to 10% if you consider like wait staff, you know, like for restaurants and that kind of thing, and grocery workers or something like that, you know, people and or transportation sector. So it depends on how big you want to make your box. And if you want to argue just farmers and people that work directly in factories that make food, it's going to be closer to 2%. So, and 5-ish% is kind of what people like, oh, let's split the difference. So, so yes, we are all right on that. Anybody want to guess what the percentage of the population geared towards food production was before the Industrial Revolution? Nope, a little higher. It's 50%. Good guess though. It took about half of the world's population was directly involved in food production. And the point of that is that so the half the population before the Industrial Revolution was directly involved in food production, and that freed up the other half of the population to do other things. So you would have the artisans, you know, the carpenters, or the lord of the manor, the bricklayers, the soldiers, the knights, or I don't know how you want to put, whoever you want to put that, you know, the different classes of people, gladiators, chariot racers, you know, but they were all, the reason why they could have those jobs was because half the population though was directly involved in food production. Now we have, you know, depending on the arguments, the ones directly involved in the industry, sort of in the 5-ish% range. So instead of one every 2 people, it's about 1 in every 20 people. And then because of this, society has changed. So, I mean, although we have an ag program here at this college, you know, most of us are not dealing directly with food production. We have other jobs. And also our economy has changed. Even in the United States, we have a service-based economy. I mean, I'm in the service sector, right? I'm providing a service to you guys. I'm an educator, right? And everyone, I mean, most people are providing some service, right? So mention pharmacy. Pharmacy is a healthcare industry. That's a service industry, right? So it's our economy has very much changed because we have our food production mechanized. And so when it comes to, and I guess even backing up, I'm bringing in philosophy. Has anyone ever heard of a Malthusian catastrophe before? Have you ever heard of Thomas Malthus and a Malthusian catastrophe? You have, okay, oh. Yeah, so food production, so number and time. This is food production. So food production, and if you look at how food is produced, it tends to follow a linear fashion, right? So meaning if I plant 1 acre of corn, I get 100 bushels of corn. It's more like 500, I think, but let's say I want 200 bushels. What do I have to do? I have to plant 2 acres. And if I want 500, I need to plant 5 acres. So it's a linear function. Population, on the other hand, is geometric. So population is geometric, and you get to a point where your population has grown faster than your ability to feed yourself. And that circumstance is known as a Malthusian catastrophe. So, and the other thing with, if you look at population, if you look at the human population versus time, it kind of flatlined and it's gone up. So around the year 1900, we were at 2 billion people. And now what are we at, like 7 or 8? So we're at 8 billion. So, and by doubling, so remember talking about growth rates and stuff. I mean, the population has doubled twice in 120 years. So in 60 years, we have had a doubling. And before that, I think it was around like, I want to say like 1000 AD or something like that. So it took us 1,000 years to double our population before, and then after 1900, our population doubled in 60 years. You know, that's quite a jump in increase in rates. And why have we had this huge jump in population? And the answer, there's a wide variety of reasons. The main answer to me is twofold. One of them is food production. We industrialize our food production, and so that means we use chemical fertilizers. We use chemical agents, so pesticides. So, I mean, not was just looking at this as a historical document, but if you've read things in the Judeo-Christian Bible, they talk about plagues of locusts and these kind of things. And a plague of locusts is very dangerous because it can wipe out a crop. And if you wipe out your wheat crop, you don't have bread for the next year. So what do we do now if there's a swarm of locusts? We gas them with organophosphates, and literally use nerve gas and they all die. Right? So swarms of locusts are not a problem anymore because we will kill them very easily. And so not only that, we use fertilizers, and our crop yields, our food production was no longer arithmetic, it was geometric. We produce food. The crops yields right now, they're on steroids. So if you look at the roots, if you compare like corn and wheat, the roots that for the way that we have crops now versus crops that are raised without synthetic fertilizers, it's huge. I mean, the difference is just enormous. So our food production is so huge right now. And not only that, we have an issue with obesity, right? We have so much food, we're too fat. So that's how much food we're producing. And do you remember what I mentioned last semester? What was the other reason for our population jumping up so high? You don't. No, it's fine. I'm just teasing. My opinion is the invention of antibiotics. So, I mean, some people thrown vaccines into that too. And vaccines are wonderful, and they've saved a lot of lives, but I think antibiotics have saved more lives than vaccines. Because if you look at what causes death right now, I mean, our age, most common cause of death is murder and suicide. You know, but if you look at what takes people in general, the number one killer is cardiovascular disease, heart attack, stroke. Number two is cancer. So, I mean, that's what kills people now is you get old and then you die of some sort of cardiovascular ailment and or cancer. So, and if you don't die from that, you die from like, you know, accidents and or from other humans. So of course that's gone up in the recent years because of COVID, but infectious disease tend not to kill people. But still, even with the height of the pandemic, there's still more people died from cardiovascular issues than they did from COVID-19. And I'm not trying to downplay the pandemic. It's a horrible disease, but it's infectious disease still is not the number one cause, even in the midst of the pandemic, for human death. But what antibiotics have done, though, is it's prevented death from certain diseases, mainly pneumonia, sepsis, and those types of, you know, the nasty bacterial diseases. I mean, a lot of people died of pneumonia back in the day. A lot of people died of sepsis. People still die of sepsis. It's not as common. So, not only that, the people that were dying were in their reproductive ages. So most people, as they're dying now, are beyond their reproductive ages. Well, at least I know women tend to lose their reproductive ages in their 40s and 50s, but I mean, men can be, but fertility also goes down for them. But since we have more of the population surviving during the reproductive years, there's more babies, kind of thing. So lots of food, lots of people that are surviving. So we had this huge jump in population. And I'll get to this later. The number one that we use for fertilizer, it comes from ammonia. And it'll be interesting to see how this plays out, because Russia is where we make most of the ammonia. So we'll see what's going to happen with the war coming and the sanctions. I mean, right now the sanctions allow the transport of energy. So, but not no one's mentioned ammonia yet. So that will become interesting in the future. We'll see. So sulfuric acid fertilizer, and I mentioned the importance because our industrialization of our agriculture now is one of the reasons why we have so much food. So fertilizer, specifically fertilizer, is the second most chemical that we make. So synthetic fertilizers is the second highest in terms of volume and mass of all the chemicals that we make as a society. Can anyone guess what number one is? What? It's not soap. Good guess though. Fuel. Fuel's number one. Fertilizer's number two. So sulfuric acid, battery acid, and a very common fertilizer is ammonium sulfate. So ammonium sulfate is a very common fertilizer, and that's made from 2 parts ammonia to 1 part sulfuric acid. So very, very important. So Also used to make explosives, more commonly also used to make nitric acid, but well, ammonia more often is used to make nitric acid. Dye, glue, batteries, I already mentioned acid batteries, and copper. Oh yeah, you can turn it into copper sulfate and electroplate stuff with that. Then moving on, nitric acid. So nitric acid is pretty scary. So it's not the scariest, but it's difficult to handle. Nitric acid. So the way you make nitric acid, okay, I guess the way you make sulfuric acid, we make it from sulfur. So you basically take sulfur, you burn it. So I'm not exactly sure how we make hydrochloric acid, to be honest with you. Nitric acid, we make it from ammonia. We take ammonia, we oxidize it, and you mix it with water, and you get nitric acid. So, and a very common fertilizer is ammonium sulfate. I'm sorry, ammonium nitrate. Ammonium sulfite is a very common fertilizer. Ammonium nitrate is another one. It's a very common fertilizer. And explosives. So nitric acid is a scary stuff to work with because you can make explosives very easily. So, so some of the explosive, you ever heard of TNT before? How do you make TNT? Does anybody know what TNT stands for? Trinitrotoluene. So the way you make TNT is you put toluene in nitric acid. And toluene is it's a hydrocarbon. It's an organic molecule. Also dynamite. The active ingredient in dynamite is nitroglycerin. So hear the word nitro. Nitro means explosives. And how do you make nitroglycerin? You take glycerin, which you get from soap, and you mix it with nitric acid to make nitroglycerin. So the issue with nitric acid is if you mix it with stuff, you tend to make explosives. So it can be scary. Like if you have it in the lab, I mean, you don't want to have nitric acid in an organic chem lab because if you start mixing things together, you're going to make explosives. And some of them are shock sensitive. TNT is not, but nitroglycerin is. So I mean, you can actually take it and smack it, and it can blow up. I think that's what they wouldn't let liquids on planes anymore. I think that's what they were trying to do, was trying to make nitroglycerin. Because if you have a water bottle of nitric acid, a water bottle of glycerin, you take it, you mix it together, shake it up, and you could blow a hole in the side of a plane. I mean, you would take yourself out, but you would, it would work. It's shock sensitive. But interesting with nitric acid and nitroglycerin. The inventor of dynamite was a guy by the name of Alfred Nobel. So he invented dynamite and he made a lot of money. And dynamite's still used today, used to blow up like patches for roads, for buildings, and also at the time, railroads it's easy you can hammer a little hole into a rock, put a stick of dynamite in there, have the dynamite explode, whatever, light the fuse, run away, it explodes, and then clear out the rocks and keep on doing. That's the way they can make tunnels. So specifically for railroads. And so nitroglycerin, very, very shock sensitive. Dynamite, not shock sensitive at all. Saved a lot of lives. But also, of course, dynamite was used in warfare. And Nobel was called the doctor of death. He was a profiteer from this. He was making tons of money. And he goes, you know what? I don't really want to be known as the doctor of death. He's also Swedish, by the way. He was a Swedish guy. And he was like, I really don't want to be remembered for warfare. So he hired a bunch of people to be a think tank and said, what can I do to prevent myself from being known as a doctor of death? And then they go, well, what you can do is set up a trust fund. And that trust fund, you will have a panel of people that will pick someone who is the epitome of peace in the world. And then have that person get the Nobel Prize for Peace. And you will forever be associated with peace and not with war. So that's what he did. And the other thing was Of course, there's other he expanded the trust fund to have other Nobel Prizes. There's economics, literature, physics, chemistry, and physiology, and peace. So the non-peace ones are given out by the King of Sweden. So, but the Peace Prize is given out from Norway. So Norway at the time, some argue still is like the peace-loving hippies of Europe. They were the like I said, the super like peace-loving folks. So they are the ones that well, they control the Norwegians or the panel of Norwegians. I don't actually who is in it, but they're the ones that give out the Peace Prize, or at least decide who gets the Peace Prize. So the rest of them is from, and it's a committee, but it's gifted by the King of Sweden. So it's interesting. Yeah, dynamite is actually the source of the funds for the Nobel Prizes, and it worked, right? I mean, we don't think, when we hear Nobel, we think of the Peace Prize usually. So it's kind of and the Peace Prize is in some ways is the highest honor you can get on the earth. So that's good marketing. So, but that's nitric acid, and the ammonium nitrate. This is a fertilizer that can be used as an explosive. It's a very common fertilizer. We put it on crops, right? But I mean, it's what ammonium nitrate can be used and is used as an explosive. It's a cheap explosive. It's fertilizer, right? I mean, dynamite. It's nitroglycerin, which is difficult to make. Well, I guess it's easy to make, but it's still shock sensitive, But you take dynamite it's basically clay plus nitroglycerin. So that's a little bit more involved. Hey, it's just fertilizer. All we need is fertilizer and a little bit of oil and like a blasting cap, and we got ourselves a bomb. So, and they use this a lot for roads and buildings and whatnot. Of course, it's been used for nefarious purposes. And this is hard to control, right? Because it's fertilizer, right? I mean, so a farmer goes and buys 200 tons of fertilizer. FBI shows up. Where's the bomb? I'm like, what bomb? Where's all the fertilizer? I'm like, it's on the corn. So it's hard to control this. And okay, so acetic acid, that's in vinegar. So citric acid, and that's in fruits. So specifically citric fruits, and we use it to get the pH right in foods, and also so magnesium citrate, calcium citrate can be used as buffers. We haven't talked about buffers. They regulate pH, and we can also take the magnesium citrate, calcium citrate for antacids. Carbonic acid. This is in fizzy water, any fizzy water. So it can be sodas, can be beer, can be champagne. That's all carbonic acid. Our bodies also use this. I'll talk about this. I guess I talked about it a little bit. This is how we transport carbon dioxide, so to our lungs. So CO2 plus water is in equilibrium with carbonic acid. And we have hemoglobin to transport oxygen to our cells, but carbon dioxide, when we oxidize it in our mitochondria, oxidize our fuel, mostly glucose, it releases carbon dioxide and water. Carbon dioxide dissolves into the cytoplasm, and then the carbonic acid is transported outside the cell, just by dilution, concentration, not actively transported, and then goes in our bloodstream. And then when our lungs exhale, carbon dioxide pops out. So that's how we transport it via carbonic acid. Ooh, hydrofluoric acid. This stuff is scary. So frosty glass. So metal cleaning frosty glass. Has anyone ever been to Iolani Palace on Oahu? You've seen the frosty, the pretty windows that have like the ladies on it in the front of it. So if you don't remember that, it's the way that you frost glass. What's that?
On the outside?
Yeah,
Oh yeah, I've seen that.
yeah, that's the way that you make that is you take glass and you put hydrofluoric acid on it, and it turns it frosted. So hydrofluoric acid, though, it's so I'm scared of this stuff. I'm really afraid of this stuff. It's a surface, it's a skin anesthetic, so you can't feel it, and it's bone seeking. So let's say, and I had a friend in grad school. I guess he was working with some of the stuff, and then he heard something like he had like white foam in the back of his hand, and because the hydrofluoric acid, he didn't feel it, but it was the acid was dissolving his bones, and this stuff is very dangerous. And then, well, he had the cure for it is calcium glutamate, and it's in a lotion. He was rubbing that on his hand, but I mean, he was a little freaked out because if you can get bone chips, like if that happens, you can get bone chips, and the bone chips can go into your heart, cause a heart attack or a stroke. So for a healthy individual, so very, very scary. Very, very hard to work with, and it dissolves glass. So hydrofluoric acid has to be in plastic containers. So if you go in the stock room in chemistry, a lot of our acids are in glass containers. So at least the bulk stuff, hydrofluoric acid, it'll eat through glass. But we also use it in our chip manufacturing. The way that we make microprocessors, I guess they're nanoprocessors. You take silicon, you have a silicon wafer. So you're gonna get so metallurgy grade silicon by just taking silica sand, melting it, and sticking carbon in it, and you get 98% pure silicon. Then you take that silicon, you dissolve it, I think with hydrofluoric, and then you can precipitate out electronic grade silicon, which is going to be 99.9% pure silicon. So, and you get these sort of long ingots of that, and you can take that with usually a diamond saw, and they cut it into thin, like, circular wafers. And you take those wafers and you have a press, and you press the image of the transistors that you want for your microprocessor. You press it down and it oxidizes the surface under vacuum. Then you take that wafer and you stick it in another chamber, and you put in fluorine gas and ultraviolet light. And we think what happens is that hydrofluoric acid is formed. It eats away the silicon, and then you take that out, and then you strip off the oxide layer on the surface, and now you have the silicon transistors that are like hundreds of nanometers wide. I mean, so that's how we make our processors now. So and I'm saying we think, because we haven't really looked at it. There's not anything published on it, because much of what the semiconductor industry does is trade secrets. The other thing is fluorine is just, it eats everything. It's very, very reactive. And if you are going to do research on fluorine, you're going to have to replace your vessels. And semiconductor industry has a lot more money in academia. So they have to replace their reactors quite a bit in the semiconductor industry, because of the fluorine that they use to eat through the silica, the silicon. And one of my sisters, I have three sisters, but one of my sisters, she's an environmental engineer, and she used to do audits for companies, and she was at a metallurgy plant one time, and one of her colleagues was there inspecting, and she got splashed with something that might have, and they thought that it had hydrofluoric acid in it. So what they did was they hosed her down, like, chemical shower, removed all of her clothing, and then they put her in a body bag and took her to the hospital for evaluation. So she turned out to be fine, but can you imagine that would be a rough day, right? I mean, they did it. They did it properly, right? I mean, you get splash, the chemical splash, especially something that can, you know, dissolve your bones and you don't feel it. So, I mean, that was the proper procedure, and they did get her evaluated. She was fine. She did not get an appreciable dose. But man, like, to me, that's the reason why I think it's scary. That's a scary chemical. And so phosphoric acid, so fertilizer, so plants, they have the macronutrients for plants. So we humans, we need a lot of carbs, carbohydrates, proteins, and fats. Those are our macronutrients. Plants, their macronutrients are nitrogen, phosphorus, and potassium. And so the ammonia, that's nitrogen. That's the biggest one. That's what they of those, kind of like we humans eat a lot of carbs. So the plants need a lot of nitrogen, and that's the big fertilizer. But also phosphorus is important, and phosphoric acid is one of them that you get for fertilizer. And it's also used as a preservative. So bases, so I guess I should mention what an acid is. That's not moving. It freeze. Okay. Acids, acids, they add positive charge. If you want to break it down, acids add positive charge, bases add negative charge. So that for aqueous reactions, it's the hydrogens. That's the source of the positive charge is the hydrogen. So acids, they turn litmus red, and you can see that we oftentimes have the acids written in red because they turn litmus red. So litmus is it's a dye. It's an indicator, and it turns red with acids, and then it starts to turn orange and yellow and kind of green around 7, and then blue around 8 or 9, and it's really blue at 14 for pHs and 14. So I haven't talked about pH yet, but I think a lot of people know what pH is, but I will talk about that soon. Litmus turns red in acid, blue in base. Acids taste sour. So right, when you think of citric acid, it's kind of a sour flavor. Same thing with acetic acid, right? You're sipping on vinegar, you're like, ugh, sour. Same thing with citric acid. So think of lemons and limes; those are really high in citric acid, right? So sour. And bases taste bitter. So bases taste bitter, and but almost all foods are acids. So I even was curious because of bitter melons, and I checked bitter melons, and they are in fact acidic. So the flavor, I don't know where the flavor of bitter melons is, but I can tell you it's not from its pH. But bases taste bitter, and so what's the bitter flavor? So another word for basic is alkaline. And there are plant chemicals called alkaloids. Alkaloids are alkaline chemicals, basic chemicals. Basic, I mean opposite of the acid, basic chemicals that plants make. And caffeine is an alkaloid. So if you drink caffeine, the bitter flavor that's in coffee, that's from the caffeine. So that's the bitter flavor. And generally speaking, humans don't like bitter flavors because they're poisonous. So things that are bitter tend to be poisons, and also poisons tend to be basic, alkaline. And so, I mean, it makes sense that we humans are like, this thing is toxic, I love it, right? So no, we tend to not like it. So like a really heavy cup of coffee is going to have like on the order of 100 milligrams of caffeine. So milligrams, right? So this is different than the 20 grams of sugar that you get in your sodas, right? So milligram. So so that's why, right? Caffeine's pretty toxic. I mean, it's okay in small quantities. Like many things are okay in small quantities, but it's fundamentally toxic. So, but okay, and So other bases, so sodium hydroxide. This is also known as lye. So if you've heard of lye before, that's usually sodium hydroxide, also called caustic. So caustic, if you say, you can use caustic as an adjective, and you can also use it as a noun. So I guess it can also be contextual, because you can say, this is a caustic solution. You could mean, usually when you say caustic in that regards, usually adjective, but you can say this is 50% caustic, 50% sodium hydroxide, or 50% lye. These would all mean the same thing. But caustic also in the colloquially, right? You're like, this person is caustic. You're like, we don't think this person is made of sodium hydroxide. No, that's not what we're saying, right? It's because lye, it hurts. I mean, basic burns. I'm more afraid of bases than I am of acids, except for hydrofluoric acid. I'm really scared of that. But base burns, you can't feel them right away. So acid burns, it hurts right away. So especially sulfuric acid, that stuff feels like a bee sting. Whew, that stuff hurts. But like sodium hydroxide, you don't notice it, and then it starts to itch and tingle, and then it really starts to hurt, and you get a blister. It hurts even more. So, and it's really painful. So, and one of the ways you can tell if something is, if you have a base burn, is if it feels slippery on your skin. So if you rub your finger, like if you get something in your hand and you rub it together, and if it feels slippery. So if you're at home and let's say you're working with bleach, like I do this sometimes, so I'm working with bleach. I'm like, did I get bleach on my fingers? And what I'll do is I'll rub my fingers together. I'm like, oh, it's slippery. Then I guess you run your finger. The MSDSs say to do it for like 3 to 5 minutes. Usually I find 30 seconds is enough, but you can tell, just check as you're running under flowing water. You can rub your finger together. If it stops becoming slippery, then you're like, okay, it's gone, kind of thing. So, but base burns, these are horrible. Have you ever seen the movie Fight Club? You ever seen that movie? Or I don't know, it's maybe they put lye on the back of their hands, and it creates a blister. So, and usually takes a bit of time. But anyways, sodium hydroxide used for various things. Petroleum, especially making biodiesel, and soap, used for a lot for soap, plastics. Same thing with potassium hydroxide. So for cotton is a huge crop. I mean, the biggest crops that we have are corn is huge, wheat is huge, soybeans is huge, and cotton. So those are kind of the crops that we have in huge amounts. Cotton, of course, for clothing. Most of what I'm wearing is cotton, right? My shirt and jeans, these are all cotton. So, and potassium hydroxide is also, a lot of liquid soaps are potassium hydroxides. So at least soaps made from potassium hydroxide, especially Castile soap. A lot of times that Castile soap is made from plants. So potassium hydroxide plant soap is Castile soap. Oh, and batteries, alkaline batteries. So you've heard the word alkaline batteries before. They tend to have potassium hydroxide in them. So be very careful if you do take apart an alkaline battery. That's kind of cool. Like if you ever take like a hacksaw and saw it in half, and if you do that to a battery, you'll see this gel inside of it. Don't touch that gel and touch your eyes. That's a bad idea. So and be careful of that gel. So same thing with batteries. Sometimes they start to leak. If they're old, they kind of expand and they start to leak. You can have potassium hydroxide there, so be very careful with those. And sodium bicarbonate, that's baking soda. So we use that. I use it also as a toothpaste. And sodium carbonate. So, oh yeah, this is also, sodium carbonate is also known as washing soda. So used in a lot of laundry detergents. OxyClean, if you ever know what OxyClean is, it's sodium carbonate with hydrogen peroxide stuck in it. That's why, that's OxyClean. So making glass, ooh, and the ancient Egyptians figured this out. If you take silica glass and you mix it with sodium carbonate, it melts at a much lower temperature. So that's how they've made glass. And we still, much of like the artisan glass and the cheap glass, like the glasses that you have, like you buy from like, from Ross or something like that, just like the pint glasses. That's going to be sodium carbonate glass. A little more expensive is Pyrex. That's borosilicate glass. There's other types of glasses, but the cheap glass and the artisan glass is all sodium carbonate. You ever seen the show Blown Away on Netflix? I like that show. But no, I haven't seen that. Okay, yeah, when you do the decorative glasses for like the glass blowing, it's going to be sodium carbonate. Ammonia I mentioned, and so it's interesting how ammonia in its chemistry is very political, and it's used a lot in warfare, obviously. So ammonia is what allowed Germany to fight World War I. So when we were around the year 1900, the leaders of the world knew about the Malthusian catastrophe, and this is when hungry populations tend to revolt. So when populations become hungry, so they tend to overthrow their rulers, and this is one of those, we have a problem, folks, we have a problem. And what they were doing is they were mining so nitrates in South America, and they were putting that in the crops, and that's how they were sustaining it. But of course, mining, eventually they run out, and like, well, we're going to run out of this stuff soon, or at some point in time, so we need to find a solution. And we went through a bunch of different ways to make nitrogen here, and actually in I should say in Canada, well, around Niagara. They were using electronic discharge, so just making lightning bolts from the hydroelectric plants up and around Niagara, so to crack nitrogen that way, to form essentially a cyanide, and they were putting cyanide on crops. Also got rid of the ant problem, I'm sure, or cockroaches, but because also the blue-green algae, also known as cyanobacteria. So it's cyanobacteria can make cyanide groups, which is also fixating nitrogen. So which is good. A lot of crops do this. Well, specifically cyanobacteria does this. So and then that's how one of the ways that nitrogen is naturally put into soil, nutrient soil. Of course, we use ammonia, and ammonia was figured out by a company, if you ever heard of it, called the BASF. They're a chemical company. So in the United States, the biggest chemical company is called Dow. And BASF in Germany, they figured out, and it was a guy named Carl Bosch. He took the research of an academic, Fritz Haber, Aber, I guess is Aber, and so sorry, someone's messing with me at the door. Haber was using osmium to make ammonia, and osmium is more expensive than gold. So Carl Bosch said, well, using a catalyst, like, well, I need to find a better catalyst. And what Carl Bosch figured out, and I don't know how, he just tried a bunch of them. So like the legend with Thomas Edison and the light bulb, but he found out that if you take iron ore from Sweden and you heat it for 8 hours in the presence of hydrogen, it makes a good catalyst, and it's cheap, it's readily available. So, and then Germany made a lot of ammonia, which you can burn to make nitrogen oxides, which you can then make nitric acid, and that means you can make explosives. So when World War I started, so Germany invaded Prussia, Poland, and started World War I. And so Britain had the biggest navy in the world at the time. Britain said, well, this is an easy war. blockade. They're not getting any fertilizer from South America. Fertilizer is also used to make explosives. So no gunpowder, no crops. We're just going to sit this one out and let Germany blow up all their ability to feed themselves. And oh, but it kept on coming. I'm like, uh-oh, that's because they made it making it synthetically. So without ammonia synthesis, Germany could not have partaken as long as it did in World War I. And the Swedish ore, that was at the time, Sweden was the only place that could make this stuff. And in World War II, Hitler said, okay, he needed the ore to make his ammonia, to make explosive and feed Germany. So he brokered a deal with Sweden, so that Sweden would be neutral in the war, but they also had to provide Hitler with all the iron ore he wanted. And so they agreed. And if you know, right now, Sweden is not part of NATO. So they're one of the countries that have taken the neutral stance. Sweden, Norway, Finland, I think they're all, actually, I'm not sure about Norway. I know Finland's not, and Sweden isn't either part of NATO, but they have a history of not getting involved, but also at the same time supplying, because they're also sending aid to Ukraine. So it's kind of there. I mean, I guess I feel better about that sending aid to Ukraine than when they sent aid to the Nazis in World War II, but hey, it's history. So ammonia, very important, like I said, and because most of the ammonia in the world right now is made in Russia, we'll see what's going to happen. This is going to be important because of fertilizer. So either we're going to, depending on how long this war is going to last, we're going to either have to find an alternate source, or maybe this will be released from the sanctions from Russia. But like, all right, you can give us oil, gas, and ammonia. Everything else you can't give us. So that may happen. We'll see. So okay, how are we doing? Sorry, any questions? So, all right, so some definitions of acid. So the easiest definition is the Arrhenius acid. And the Arrhenius acid, if you throw an acid into water, it forms either hydrogen ion or H3O plus, which is hydronium ion. So if you think of water is kind of like a Mickey Mouse. So here's a Mickey Mouse there, the head with the two hydrogens. So hydronium is like Mickey Mouse with an extra ear, but also a positive charge. So it has the 3 protons, and hydroxide is like Mickey with 1 ear, but a negative charge. So the ears being the hydrogen ions, or the hydrogen atoms, the protons. So if you throw an acid into water, an Arrhenius acid forms hydrogen or hydronium. You can model it as a hydrogen ion. Actually, this is something that we actually don't know. We don't know if there's a free hydrogen ion, and we don't know if there's hydronium ion. If you read the book, it says that it's the hydronium, it's H3O plus. But the reason why we know this, it's from simulation. It's not real data. And so usually when we track things, we use spectroscopy. A lot of times we use spectroscopy, and we look at electrons. So a proton has no electrons. So we can't do electronic spectroscopy on a proton because there's no electrons. So, I mean, we know that there's hydronium ion. We can see that. We can see that using spectroscopy. We don't know about a hydrogen ion. So this is one of those unknowns. But the general consensus more or less is it seems to be more predominantly H3O plus. But a lot of times you'll see me not doing H3O plus because the math is easier. And I'll show you that later. So I will personally use hydrogen ion quite a bit rather than H3O plus. And same thing, base forms hydroxide. So you throw a base in water, it forms hydroxide. So that's the lowest definition of acids and bases. And the same thing I mentioned about acids, right? They taste sour, they add positive charge, turn litmus red. Bases, they taste bitter, they turn litmus blue. these kind of things. Feels slippery on your skin. So, but I mentioned the slippery part though. I mean, oils feel slippery in your skin. Oils are neither acid or bases. So they're hydrocarbons. So in order for an acid or base to happen, it's going to be, it tends to be more aqueous. So it's not going to be, for lipid solutions, you don't have a pH. So which we'll talk about later. The next highest level and kind of where we teach it is a Bronsted-Lowry acid and base. The acid is a proton donor, the base is a proton acceptor. So I am now the acid, I have my proton, I have given my proton, I am an acid. A base, now I'm going to be a base. As a base, I have accepted the proton. I am the proton acceptor. So if sorry, Zoom folks, I was miming, I was talking, I was pretending that my water bottle is a proton. So think of it like baseball. The pitcher is the one that throws the baseball, that's the acid, and the catcher is the one that catches the baseball, that's like the base, proton acceptor. And the best way to describe acids and bases is a Lewis acid and base. Lewis acid is an electron acceptor, base is an electron donor. And it works the same way, but truth be told, I tend to think of it this way. I tend to think acids this way. I mean, so the way that Lewis acids work is that if you remember from last semester, you have the bonding orbital, anti-bonding orbital. If you put electron density into the empty anti-bonding orbital, then the bond breaks. So what is happening then is that the base is giving electron density to the acid. The acid is accepting electron density, but in the process of the transfer, the electron density is added to the anti-bonding orbital of the hydrogen attached, and then the hydrogen breaks off, and then the hydrogen typically goes into the base. So it's essentially the same thing, but it's just a lot easier to say proton donor, proton acceptor versus the quantum mechanical model part. Like, okay, you have the bonding, anti-bonding orbital, electron density goes in, it pops off. It all works out the same. But I like to think of it just in terms of hydrogen's just bouncing off. So, okay. And so, have we just got questions? So here is using the Bronsted-Lowry, and you have ammonia, NH3, and notice it's blue if you are not colorblind, because we tend to put bases blue, acids red because of litmus. So we have ammonia base plus water acid, and an acid is a proton donor. So you can see that it goes from H2O to OH minus. It's lost a proton. That's a proton donor. It's giving its proton. For ammonia, it goes from NH3, 3 hydrogens, to NH4 plus. It went from 3 hydrogens to 4 hydrogens. It's the proton acceptor. So that's where you can find the acids and bases. So water goes from H2 to OH, loses an H. Ammonia goes from NH3 to NH4, it gains an H. Acceptor, right? So, and this is a reversible reaction. So you can see denoted by the equilibrium symbol. So if you look at this reaction going from right to left in this direction, NH4 goes to NH3. That means that NH4 plus in the reverse direction is an acid. Same thing with hydroxide. Hydroxide goes from OH minus to H2O. So accepting a proton, that makes it a base. So the forward reaction, we've identified the acids and bases, and the reverse reaction, it's the other way around. So the base will then form a conjugate acid, and the acid will then form a conjugate base. So you can see that they're the opposites. And depending on which direction the reaction goes, whether the species is it a proton donor or a proton acceptor. But we usually define them on the reactant side though. So, I mean, we call ammonia is definitely a base. So, and here's another reaction. And this is actually one direction. It doesn't go the other way. HCl plus H2O water. So hydrogen, or I'm sorry, the hydrochloric acid is going from HCl to Cl minus. It's the proton donor, it's the hydrogen donor. Water goes from H2O to H3O. It's a proton acceptor. Water is the base. So this is weird, right? Water is an acid. Water is a base. That's kind of weird. So what is water then? Water is amphoteric. Water can act as both an acid and a base. So I think one of the things I mentioned, that water is a weird chemical. Water is a really strange substance. And one of the reasons why it's weird is because it's amphoteric. So it can be an acid or base. Doesn't make up its mind. It's very contextual. It's like I can be an acid in this case, I can be a base in this way. Water is not the only amphoteric stuff out there. So amino acids. Amino acids, they're also amphoteric. So it's not like it's so weird. We never see this ever again. No, that's not true. Because like I said, amino acids and right, amino acids are very common. It's what makes up protein. So everything you're looking at now, at least that's me, you know, is protein. I guess maybe not my eyes. My eyes are tears. The surface of my eyes are tears. And then you have the cell membranes. So, but anyways, except for my eyes, if you're looking at me, I normally see my teeth too, but I have a mask on. So my hair and skin is a protein called keratin. It's all amino acids. So, okay. All right, so identify I guess I should have erased this. So identify these as acids and bases. So I just keep it as is. So starting off with H2SO4. Actually, maybe I can use red. H2SO4. So it goes from H2SO4 to HSO4. So it loses a hydrogen. So meaning it's a hydrogen donor, proton donor. So proton donor makes it an acid. Water goes from H2O to H3O. It's gaining a hydrogen as a proton acceptor. That makes water a base. And then the opposite direction. So the HSO4 minus goes to H2SO4. It's gaining a hydrogen. It means it's a base. But it's on the other side of the equation. We call it the conjugate base. Same idea with the water. Goes from H3O to H2O. It loses a hydrogen. Proton donor. So it's the conjugate acid. And then the other reaction. So bicarbonate ion goes from HCO3 minus to H2CO3. So it gains a hydrogen. That means it's a proton acceptor, it's a base. And then water goes from H2O to OH minus. It's donating its proton, it's the acid. So questions with this so far? All right, let's see if you get this reaction. Carbonic acid plus water in equilibrium with hydronium and bicarbonate ion. Which one is the conjugate base? And the base is the proton acceptor. How many think A, carbonic acid? I think B, water. I think C, hydronium. I think D, bicarbonate. So people are not, some people are, we got to vote for C, vote for D. So the So the conjugate's going this way. So it's going to be one of these two. And this direction, a base is a proton acceptor. Right? So if you look at, so HCO3 minus plus hydrogen goes to H2CO3. So this one here is a base, and it's the conjugate base because it's on the right side of the equation. So it's that one. Does anybody have any questions with that? The hydronium is an acid because it goes from H3 to H2. So I guess I keep on. Maybe I should just break it down more simply. If you have a base is going to gain an H, an acid is going to lose an H. So HCO3 goes to H2CO3. It gains an H. It's a base. So, make sense? Okay. So, I normally don't tell you to memorize stuff, but the easiest way to do this is to memorize the strong acids. And if it's not one of the strong acids, then it's a weak acid. So the strong acids are hydrochloric, hydrobromic, hydroiodic, nitric, perchloric, and sulfuric, but only the first hydrogen for sulfuric. So, and hydrofluoric acid is not a strong acid. So strong acids mean that they completely disassociate. And a weak acid means that there's an equilibrium. So in weak acids, they're pretty tightly bound, actually. We'll get into the math. I don't think we'll get into it this class, but next class we can talk about some of the equilibrium numbers. But weak acids, they like to stay molecular. So well, as you know, I think I've mentioned I'm married, and I remember on my honeymoon, it was a wonderful time. My wife and I were like weak acids. Okay, weak acids like to stay together. We weren't together all the time, right? So if we were out and she had to use the restroom, right, she would go in the ladies' room and I would go in the men's room, right? But when we came out, we were back together, right? It's kind of thing. So we were always together, and not always, but you know, you found us together most of the time. And that's the same thing with weak acids. They really like staying together. And occasionally you'll see them apart. So that's the equilibrium. We can show that more later. Strong acids, they are not bound at all. It's like if you've ever done like this pre-pandemic times, but it's kind of the equivalent. It's like the chemical equivalent of like Google Uber carpooling. You ever do the carpool and Uber? If you've ever done those, that you don't get your own Uber, but you get like, you share it with like 4 or 5 other people, and then they drop you off, and maybe you talk to the people in the car, maybe you don't, but right, it's just a matter of convenience. So hydrogen and chlorine, they don't really care for each other. They're hanging out. Once they get to the destination, they fly apart. Like, all right, hydrogen, you go this way, chlorine, you go that way. I'll never think of you again, kind of thing. So whereas weak acids, they're the sappy couples. They're like, no, where are you going? I want you back. I want to stay joined to you. So that's a weak acid. It's a strong acid, completely flies apart. And so, and that's why I have this arrow. That's why I have this solid arrow going that way. Hydrogen and chlorine, it completely breaks apart. And you notice that these are the halogens: hydrogen chloride, hydrogen bromide, hydrogen iodide. Actually, I guess I can also call them acids: hydrochloric acid, hydrobromic acid, hydroiodic acid. So hydrogen fluoride, though, so hydrofluoric acid, it's an acid, but it's not a strong acid. The reason why is because it forms a dimer. So two mers, di to mer molecule. So hydrogen fluoride, it's got the hydrogen bond, and it attaches to itself, and then it creates the dimer, the two molecules, and it doesn't rip off the hydrogen as easily. So it tends to stay more molecular than it does breaking apart. So then nitric acid, and you can maybe notice that these acids, these are also known as oxyacids. They have a lot of oxygen. So 3 for nitrogen, 4 for chlorine, 4 for sulfur. So perchloric, not used as much. Perchlorics, they tend to form explosives. Nitric also form explosives. Sulfates, not as much. But perchlorics and nitrates tend to be very explosive. They did this in Hawaii a couple of years ago. They banned the use of perchloric fireworks and for the big displays. So like, I've never been here for New Year's Eve. Do you guys blow up a lot of fireworks? Does it get really smoky? Okay, so I've been on Oahu for New Year's, and I'm usually out somewhere either in Asia or in the mainland for New Year's. Like I haven't experienced New Year's here in Hawaii or on Maui, but it's all that haze. They tend to be perchlorates from the perchlorate fireworks. They're kind of dirty. Nitrate ones, they're a lot more expensive, but they're not as smoky. And if you've noticed firework displays now, we're having fewer firework displays even before the pandemic. We're having fewer firework displays, but you also might notice they're not as smoky because they're using nitrates, and then they're more expensive. But anyways, yeah, so the weak acids though, so strong acids associate weak acids form equilibrium. And so and this reaction, as I've written this top one here, this is known as a hydrolysis reaction. So reaction with water. And so weak acid HA plus water makes hydronium ion plus acid anion, the conjugate base. And then the Ka is the hydronium concentration of the conjugate base all over the acid. It's easier for me. I tend to write it this way just because it's one less line, right? It's just, in a way, it's one less thing to worry about. So you can do either way. I tend to do it this way. The book tends to do it this way. We'll eventually get to electrochemistry. Electrochemistry does it this way. So, I mean, they're considered equivalents. So, and I have some professors, they are so like no, you must teach it this way, and I don't. So it depends on who you have. Oh, and so for sulfuric acid, the first hydrogen is strong. So sulfuric acid is a diprotic acid, 2 protons. The first proton is strong, but the second proton is weak. So meaning it's in equilibrium, but it's still pretty strong. But we'll do some calculations with those later. So here are some other weak acids, and my shut up alarm is about to go off. But I've already mentioned all of these as well, except for formic acid. Formic acid, that's the acid that's in ant bites. So if you've ever, formis is the Latin for ant, and like the antacid, like antacid is they use for their toxic, their venom is formic acid. Anyways, okay, that's my shut up alarm. So it's time for me to shut up. Anybody have any questions? All right, let me know. It's office hours, of course. I'll stay behind, but class is over and I will stop recording.